Today we're going to talk about resistance and resistivity, and we're going to I'm going to show you this little equation right here, which is basically the resistance of a resistor is equal to the resistivity, that's what that rho stands for in this context, the resistivity of the material times how long the material is divided by the cross-sectional area of that material. So that's our goal. That's what we're going to get to by the end. And but first we're going to review Ohm's Law and then talk about resistors in a DC circuit, and then we'll talk about resistivity. All right. So we did this last time. We derived Ohm's Law. And so let's review it, though. If I've got like a battery, sometimes you'll see it drawn like this, like there's two cells in series with each other, which I showed you last time with the, and then we hook up some wires. Now wires have resistance, but we're going to say that for this circuit, the resistance of the wires is so tiny that we're going to ignore it. Then we have some kind of device. Could be a light bulb, which we did last time. I showed you last time anyway. Or it could be an electric motor, something that's using the energy that's being carried by the electricity, by the flow of charge, and removes that energy from the circuit to do something, hopefully something that we want it to do, like to create heat, like the elements in a toaster. Those resistors in there get really, really, really hot, so we can toast our bagels. It's very important. And then, or it can turn an electric motor, or it can make a screen on a cell phone. That's use of energy. So we call all those things, all those devices, resistors. And so let's suppose that we have a, let me see how I want to make sure I stick with the right, yeah. So this we're going to call this delta V here. This is a change in voltage due to the battery. Sometimes you'll see it with a curly E like this. They mean the same thing. This is how much energy per unit charge we're going to get out of a battery. Now most little electric cells you put in a flashlight are 1.5 volts. Put two of them together in series, you got 3 volts. Put a whole bunch of them in series together and you got a whole bunch of volts. Okay? And then the charge that's going to push current through the circuit. We call current I. And this, let me go over that. This is volts, which is joules of energy per coulomb of charge. So that's how you measure the battery. The battery, it gives the charge carrier some energy, and that energy is carried through the wires to our object with the current. And the current, well, that's the rate of change, delta Q over delta T. That's the rate at which charge is going by in that circuit. And of course, this is a coulombs per second. And remember, a coulomb of charge is just a gigantic basket of charge. But if you have 1 amp, you have 1 coulomb of charge going by every second. Now, we were screwing around with the robot this weekend, and there was something wrong with the gearbox, and I think how many amps was that thing drawing?
107.
107 amps. Isn't that a little high?
No, that's fine. Don't worry about this.
Yeah, that's why magic smoke starts coming out of the. So yeah, that's what don't worry about it. Like, that's a lot. Now you might think, well, I mean, a coulomb of charge is a huge amount of charge. If I were to, try to fit a coulomb of charge on the end of this pencil, well, this would be a bad day. I'm pretty sure I would be electrocuted by the sparks coming off of this thing. It would be lightning bolts. A coulomb of charge is tremendous. But in a wire, remember, wires are electrically neutral. They've got just as much positive as negative charge in them. It's just that those outside electrons are free to flow. Now, those free to flow electrons aren't moving this way. The electrons are actually moving this way. But we define current to be the flow of positive charge. So, so if the current is, we say the current is flowing this way, well, the electrons are actually flowing the other way. But it turns out happily that all the mathematics and the equations and our analysis of circuits works just fine if we pretend that what's actually happening in a circuit is that positive charge carriers are moving through the wire. But that's all pretend, because it's really negatively charged electrons that are moving the other way. And again, as I said, blame Benjamin Franklin. He had a 50-50 shot. He thought that what Benjamin Franklin thought is that if something was charged, it either had a lack of electrical fluid or too much electrical fluid. That's what he thought. Turned out to be wrong. It's sort of right, but sort of wrong. But what he thought was a lack of electrical fluid was actually a surplus of electrons. So he got it. If only he had guessed the other way, this would be a little easier to explain. Then you got this current will flow through this resistor, and that resistor will send the energy out of the circuit at a certain rate or power, and then the energy in the electricity is back down to zero. So here we're going to say, sometimes you'll see this little symbol, little ground symbol. This means this is where 0 volts. It's just the same voltage as the ground, but this comes up, boosts the energy contained by the charge, gives up that energy through the resistor, and now we're back where we started. So look, here's the thing. If this was a 12-volt battery, if I jump up 12 volts and then I come over here, guess what I have to do to get back down to 0? Pay attention to me, get off your phone. You have to jump down 12 volts. So if you're moving, if you're going around a circuit, you would say, okay, here, we're going to start here. We got nothing. We got no energy, but we go through here. Oh, this chemistry that goes on here, electrochemistry, boosts the amount of energy I contain, boosts my potential per energy per unit charge, and then I have to give it back up to get back. So if this is a 12-volt jump, this is a 12-volt drop. Always, all circuits work that way. Okay. And then, so we say, well, this has a certain resistance. And we defined resistance to be the voltage that's needed to get voltage divided by amps. How much current? Well, I mean the equation R equals delta V over I. Now, I like to express Ohm's law like this. Now, this silly, this thing expresses it like this. I don't know why. I don't see any. I see this quite often. I'll see delta V equals IR, which kind of makes sense. If you want to know what the voltage drop is across a resistor, multiply the current through it times its resistance, and that'll give you the voltage drop across the resistor. But so this is just algebraically kind of weird. It's fine. But that's a volt per amp, and a volt per amp is called an ohm. Beautiful. It's called an ohm. And we use a Greek omega to stand for an ohm, named after a guy named Ohm, physicist who figured out a lot of this stuff out. And this is Ohm's Law right here. But, you know, it's like any other little equation. You can solve for I, you can solve for delta V, whatever you need to do. Now, oh, I forgot to get some out. That's all right. That's all right. I'll just show you from the book. Resistors are we have these devices called resistors that I put into circuits. Let's say I want to control how much current a certain device is getting. I can stick a resistor in the circuit and reduce the amount of current so that, you know, maybe the device gets exactly what we want. So we put in these things called resistors, and I do have some, but there's a picture of them right here in the book. This is on page 499. And if you get bust open any electrical device, and you'll find resistors in them. You can see little pictures right here, and they look like little cylinders with stripes on them, different color-coded stripes. Now, what are those stripes all about? If you see a resistor, what do those stripes mean? Well, if you know the code, you can read those stripes and figure out what the resistance is for that resistor. Now, I'm not going to give you, we're not going to work those kind of problems, but here's the resistor code. This is also in your book. So, if you have a black stripe, well, we have different colors: black, brown, red, orange, yellow, green, blue, violet, gray, white. And unfortunately, if you're colorblind, this is why they quite often won't allow you to become an electrician, because these colors, I don't know, it's kind of discriminatory, I suppose. Now, if it's a number, black through white gives 0 through 9. So all 10 digits based on these 10 colors. If it's a multiplier, they represent a power of 10. And then the gold, silver, or no color gives us a tolerance. That means plus or minus 5% or 10% or whatever. So if you look at this, this is first digit, second digit, multiplier, tolerance. So what is the first digit? It's red. Right there is red. And so you would come over here and you say, okay, red, let me zoom out a little bit. Red is 2. Now the second one is green. So what's green? 5. So 2 and 5. So that's 25. Now what's the multiplier? That looks orange to me. So that's 3. So that's 25 times 10 to the 3. So that would be, and then the tolerance is, what is that? Gold, silver, I guess that's silver, so it's plus or minus 10%. Now let's see what it says in the description here. The resistance value of the given resistor, so this says 25.
It says that the orange one is yellow.
The orange one is yellow?
See, at the bottom of the paragraph it says green, yellow, and silver.
Yeah, okay, I'm going to stop because it doesn't really matter. I think the book might be printed wrong colors or something. 'Cause that looks orange. That's not yellow. I don't see stinking yellow in there. Liars. But that's how they do it. So if you ever get into electronics and do-it-yourself electronics, you'll have to learn that code, and it's easy. You just have a little cheat sheet next to you, and you can figure out what the resistance is. so they don't have to print it on the resistor itself. Okay. Now, so we've talked a little bit about, so most resistors look something like this. They're like a little cylinder-like thing. So here's a wire, comes into it. You might solder the wire here and the solder the wire here, and it's got these little stripes on it that tells you what it is. Now, resistors are made out of lots of different kinds of materials. Some of them are actually made out of wires. Like you might find a resistor, they just take a wire of some kind and then they wrap it around like a winding of wire, so that in a very tiny little compact device, you've got a super long wire. They got to coat it with something so it doesn't short out. And then it comes out the other end. Or sometimes it's made out of, like last year, on last year's AP test, it was Play-Doh. They made a resistor out of Play-Doh. And people are like, what? You can make a resistor out of anything. Okay, now some things have super high resistance. Let's say I've got the plastic bottle. What if I want to make a resistor out of this plastic, this super high resistance? It doesn't conduct electricity at all. So, you know, it depends on the material. But anyway, we're now gonna talk about how to set up, make a resistor. So let's say you've got some material that conducts electricity. Well, first of all, let's let me some more. First of all, let's talk about what's happening in a wire. And I'm just going to look at some chunk of wire. You learn how to do it, make an end like that when you go to Cal Poly and you have to draw this stuff. And so suppose I have a wire like this. This is just some wire, and we're going to magnify one little chunk and look at that little chunk of wire right there. Now right here, it's got some cross-sectional area. That's the area of the wire. And maybe from here to here, we're going to call it length. Now what happens when somebody turns on a switch? They establish, or you know, like a flashlight, or I connect the battery to the loop, and it establishes an electric field in the metal. So here's my electric field. What do electric fields do? They apply forces to charged particles. There are charged particles in everything, protons and electrons, in the atoms that make us and everything else that we see. And now most of them are fixed in place though, so they might have a force on them, but they don't go anywhere, they don't flow. But those valence electrons, I'm just going to draw a few of them. Why? Just because I don't have enough time to draw the trillions of electrons that are actually here. Now, if there's no electric field in here, if there's no electric field in that wire, what do? They just wander around randomly in all directions. Like if we followed the path of this guy right here, it would just be, you know, jump around like this. This electron would do the same thing, just moving around, not going. But if I put an electric field in there, what's this electron going to do? Let's take a look at this electron. Trick question, what's the direction of the force that this electron will feel due to this electric field? To the left, because it is negatively charged. So here's what it's going to do. It was moving. Somebody turned on an electric field. I know you cart people have to leave, so I'm sorry. This will be posted later. So what this guy's going to do is this guy's going to move to the left. So let's say he was moving like this, and it's just like a little projectile. And it's just going to go, whoa. But then what's it going to do? It's going to bash into stuff. It's going to hit, maybe this is copper. It's going to hit, have you ever felt a copper wire get warm? Like if you put too much current through it, it gets warm? Here's why it gets warm. Because if you put a lot of voltage across it, and you have a lot of current, that means these guys are going to bash into atoms. So bam, it bashed into an atom. Bam, bam, boom, smack, crash, boom. Every time it hits an atom, it gives up a little bit of its energy. It smashes into it and makes that atom vibrate a little bit. And when it vibrates a little bit, it's warmer, right? That's what temperature is. It's a measure of the kind of average kinetic energy of the molecules, right? So it goes up in temperature, which uses up some of the energy in the electricity. Okay? So all these guys are doing that. All these guys are drifting through the wire. We call that average speed of the electrons in the wire going the opposite way. We call that the drift velocity. And electricity does not travel at the speed of light. The charge itself does not travel at the speed of light. It goes a snail's pace through most wires. I mean, it's just really slow, millimeters per second. What is traveling at the speed of light when you flick that switch is establishing the electric field in that wire, everywhere in that wire, so all the valence electrons that are available to move start moving at the same time. It's kind of like if you have a hose filled with water and one end is connected to the faucet. You open the faucet. The pressure of that faucet pushes all the water in the hose at the same time, and that's why the water instantly comes out the other end, even though the water itself might be only traveling a few inches per second. Does that make sense to everybody? Okay, electrons are kind of like water in a hose. Okay, now, so on average, these electrons are moving through this cross-sectional area, so we say that there's current going this way. The displacement of the positive charges to the right, even though the electrons are moving to the left. And again, Benjamin Franklin would feel real bad about it if he were alive today. But not his fault, he didn't know. Now, let me ask you this. Let's figure out, let's do this conceptually. If I make this wire really, really long, is it going to be harder to get the electrons to flow through it, or is it going to be easier? Well, if I make this longer, notice that I've got, what if I make the wire twice as long? Well, let's follow one electron. If the wire is twice as long, it's going to bash into twice as many atoms getting from here over to here. Does that make sense? The longer the wire, the more obstacles are in the way of the electrons that want to move. And so you have more resistance to the flow of charge. So it turns out that the longer the wire, the greater the resistance. Oh man, I'm trying to make a video here. It's Ricky. All right. And so the longer the wire, the greater the resistance of that wire. And remember I told you sometimes they make resistors by winding up really long, taking a wire and just winding it, making super long wire that fits in a little spool. Okay, that's what they're doing. Now, here's another thing. This has a certain cross-sectional area. What if I made the wire fatter? What if I gave it what if I made the wire a whole lot fatter? Well, now the electrons have more room. And so since they have more room, it's easier for them to flow, and they won't run into as many things or to each other. And so the greater the area, the easier it is to make charge flow through it, so the less resistance there is. So the resistance is inversely proportional to the area of the wire. Or whatever, it doesn't have to be a wire. It can be anything where you put enough voltage across it and current will flow. It could be a semiconductor or something like that. Okay? Now, this kind of makes intuitive sense. All right, let's say I've got a tank of water. Maybe it's a water tower. You know the big water tower over on Villa? I think it's off of Villa. Anyway, just put a big water tower way above the ground. Way above the ground. Now, you can kind of think of the weight of this water pushing down as kind of like the voltage. Now, what if I cut a little tiny, what if I made a little tiny hole in here? And that little hole has a little tiny area to it. Do you see that you get a little stream of water coming out, right? Leaking out of that water tower to the ground? Yes? Right? Okay, everybody pay attention right now. I want you to understand it conceptually. Yeah, even you, Donald. Let's stay awake now. Fight it. Fight it! Slap! All right. Well, not that hard. I had to write a nurse pass, you know. All right, self-abuse. All right, what if I made, hey, no, seriously, what if I made the area bigger of that hole? Duh, what's going to happen? More water's going to come out for the same water pressure. This has a certain water pressure right here because of how much water there is above it. If I make the hole bigger, like that big, oh, you're going to get a whole lot more water. Same is true with a wire. If you make the wire thicker, it's easier for the electricity to flow through it, and it'll reduce the resistance of that wire. Now, those of you on the robotics team know that if you're going to have a lot of current, you have to have a certain gauge of wire to match that current. The thicker the wire, the more current you can put through it without it getting hot. So that's what's happening here. Now, think about it. In terms of the resistance of a long length of wire, that's pretty much all I can change, right? I can change the length of the wire and I can change the thickness of the wire. Now let's keep everything uniform. Now there's one other thing I can change about the wire. I can change what the wire is made out of, right? What the wire is made out of. Because all materials, especially conductors, have a little bit of resistance to them, and how much resistance a particular material has is a property of that material that we call resistivity, rho. Resistivity. And it's a property of all conductors. Now let's think about what units resistivity will have. Let's solve for resistivity here. And again, make an excellent quantity chart, you guys, when you finish this unit. Make an excellent quantity chart. You should maybe start it now. It'll really help you. So let's solve for resistivity. Resistivity, if I solve for it, is equal to the resistance, multiply both sides by the area, times the area divided by the length. Now, let's think about what units this is going to have. What units does resistance have? Ohms. What units does area have? Meters squared. What units does length have? Meters. So what units is resistivity going to have? Ohms, not per meter. Look how it cancels. Ohms times meters. Ohm meters. Ohm meters, it's hard to say that. Or you can call it meter ohms. It's a little easier to say, it doesn't matter. But you're multiplying them together. It's not a ratio, it's a product. Ohms times meter. Now this is kind of awkward to think about. I prefer to think of it as, look at the formula for it and derive the units from it. But how resistive a certain material is depends on the material. And we do experiments, and we have a table in your book that has the resistivity in it. And this is on page 501. So I'm going to zoom in here. Now, on the test for this material, I'm going to give you the resistivity, okay? Or I'm going to give you a bunch of stuff. I think on the AP test last year, you had to determine the resistivity of Play-Doh. And it was so easy. But my students couldn't do it because all right. But this year, but anyway, look. Here are the conductors. Let's take a look at silver. 1.59 times 10 to the negative 8 ohm meters. So if you have 1 meter of silver wire, it's going to have a very, very low resistance. Now, over here we have this temperature coefficient right here. We don't need that in this class. We're not going to deal with, let me focus that. We're not going to deal with how temperature affects the resistance of materials. But now look, at silver is super good conductor. How come we don't use silver?
Expensive.
It's freaking expensive. Look at copper. Its resistivity is a little bit higher, but it's much cheaper, and it's very flexible. Copper's awesome stuff. It's really good. Gold, aluminum. Take a look at aluminum. It's quite a bit more resistive than copper, but it's much lighter. So for some applications, you'd like to use aluminum wire instead. And so on. So iron, look at iron. Very, very resistive for a conductor. A lot of times they'll use iron as heating elements. Mercury, very resistive. Nichrome wires. And then we have semiconductors. Look at orders of magnitude more resistive. And then look at glass. Look at this. 10 to the negative 8. This is 10 to the 12. That's 10 to the 20 times more resistive. Yeah, these are insulators. So anyway, when you need to look up in the problems for the homework, you need the resistivity. You need that. So this is your basic equation right here. The resistance of a certain section of wire. The resistance of a wire depends on how long it is, or any material. It doesn't have to be a wire. And by the way, we're going to keep everything simple. Everything's going to be uniform cross-sectional area, a certain length, certain material. Resistivity doesn't change with temperature. We're going to keep it simple. You can figure out the resistance of that wire. Or if you know what the resistance is, you can solve for the length or the cross-sectional area. We'll give you enough information to solve this equation. But you have to know what these letters stand for. This is resistance. How many volts I need to get 1 amp of current to flow. This is resistivity. It's a property of the material. This is how long that material is, what length of that material. We got to push all those little electrons through to get them to flow. And this is area. The greater the area, the easier it is to flow. I mean, it's kind of like people marching in a line, right? Let's say you got all these people and you want to get them somewhere. Hey, Ben. If they're really, really crowded, Well, it's like traffic. It's like traffic, right? When it's super crowded, when you don't have enough cross-sectional area, they interfere with each other and stuff. So you want more cross-sectional area. So in terms of traffic, you want more lanes on the freeway. That'll allow the traffic to flow more easily. Also, the shorter the wire, the fewer obstacles these electrons are going to bash into, so the less resistance there is. And then this is just how smooth that road is. If it's a nice, smooth road, no potholes, no restricted lanes, things are going to move better. But if it's like a lousy material, like iron, I mean, iron will conduct electricity, but you pay a price. You're going to be bashing into a lot of iron atoms and heating them up. Maybe that's what you want, though. So sometimes iron is what we use. So anyway, I think we covered that reasonably well. We've got Ohm's Law, which defines resistance in terms of voltage and current. And now we have resistivity, which allows us to find the resistance of a particular device based on its length, its cross-sectional area, and its resistivity. That should be enough to get you started on the problems. That is very nice. That is it.